Imagine it, a probe with a mass of 570 kilograms hurtling toward an asteroid at 6 kilometers per second. The last images from the onboard camera show the surface growing larger and larger. Stones, boulders, dust. And then the signal cuts out. The impact happened. 11 days later, the United States Space Bureau announced the asteroid's orbit had changed. Mission successful. The first demonstration in history of planetary defense for the planet. Press conference, applause, headlines across the world's papers. But in the original data, there was a numerical signal that had not gone anywhere. And that signal said something else. Let's go through the documents. First, what Kestrel actually was, so everyone understands the scale of the task. Its full name, the Twin Asteroid Course Shift Trial, developed by the Redbrook Applied Physics Center with funding from the United States Space Bureau. Launched on November 24, 2021, aboard a Skylance 9 rocket from West Haven Launch Range in Westford. Mission cost, about $330 million. Target, the asteroid Brimor, a moonlet of the larger asteroid Halcyon. Why choose a moonlet specifically? Ease of measurement. Brimor's orbit around Halcyon can be tracked precisely from Earthmere by changes in the system's brightness. When Brimor passes in front of Halcyon or behind it, the total brightness of the system changes in a predictable way. By measuring those changes before and after impact, scientists can calculate exactly how much the orbital period was shortened. It was a very clever choice of target. No direct distance measurements, no additional probes in orbit, only ground-based telescopes. Mass of the Kestrel probe, 570 kilograms. Diameter of Brimor, about 160 meters, roughly the size of the Pyramid of King Aldrin. Only in space, in orbit around the asteroid Halcyon, at a distance of about 11 million kilometers from Earthmere at the moment of impact. Impact speed, 6.1 kilometers per second relative to Brimor. That is 22,530 kilometers per hour. The kinetic energy of the impact was roughly comparable to 3 tons of TNT. Brimor circles Halcyon with an orbital period of 11 hours, 55 minutes. That was the number that was supposed to change after impact. Minimum threshold for success, minus 73 seconds. In other words, the orbit had to shrink by at least 73 seconds from the original 11 hours, 55 minutes. The actual result after 11 days, about minus 32 minutes. The refined result by May 2023, 33 minutes, 15 seconds. Let's break down what that means. 33 minutes versus 73 seconds. In plain terms, 73 seconds is 1 minute, 13 seconds. 33 minutes is 33 minutes. A difference of 27 times. If the model predicted 1 minute and reality gave 27 minutes, that is not, we got lucky. It means the model missed a dominant physical process. That is where things stop adding up. Before we get to the beta factor, the context matters. Specifically, what the Skywatchers actually knew about Brimor before the impact. Brimor was discovered in 1996 by Skywatchers observing Halcyon. The name Brimor, translated from Greek, means having 2 forms, because at first its shape could not be determined precisely. It was too small and too close to Halcyon for ground-based telescopes to resolve it as a separate object. Practically everything Skywatchers knew about Brimor before Kestrel was its orbital period and an approximate size inferred from light curves. The first detailed images of Brimor's surface were Kestrel's images. Literally. Before that, there were none. And here is what those images showed in the final seconds before impact. Brimor's surface is covered in boulders and stones. No flat regions, no monolithic rock face. It is the classic picture of a loose rubble pile, a body with almost no structural strength. Everything is held together only by mutual gravity. But surface images alone cannot give you the full picture of internal structure. Models predicted that Brimor might be a loose aggregate, but they did not know how loose, what its porosity was, or what the friction coefficient between particles might be. Those are exactly the parameters that determine the beta factor. Now let's go through the beta factor in detail. Imagine this. You throw a ball into a pile of dry sand. The ball enters the sand, and some of the sand sprays off to the side. The ball transferred some momentum to the sand. But because of the reactive ejection of sand in the same direction the ball came from, the total transferred momentum is greater than the ball's own momentum. Beta is the coefficient of that amplification. For a completely monolithic body, like a solid steel rod, there is almost no ejecta. Beta will be close to 1. The ball hits, dents it a little, that is all. Minimal reactive ejection. For a loose pile, the ejecta is enormous. A vast amount of fine material is blasted out in the direction of impact. The reactive impulse is substantial, beta 3 to 5. Before Kestrel, physicists considered several models. The most likely one by consensus, Brimor, was a loose aggregate with beta from 1.5 to 2.5, possibly higher, but there was no hard data. Reality, 2.2 to 4.9, average around 3.5. That landed within the range that had been modeled, but at the high end of that range. This is exactly where the models erred in estimating probability. They treated values above 3 as unlikely. Brimor showed that the unlikely happened. Let's read the original. Specifically, the paper by Gareth and co-authors in Northfield Science Review, May 2023, the efficiency of the Kestrel impact in the Halcyon system. One of the key conclusions: the elevated beta value is consistent with Brimor's highly porous structure and the intense ejection of fine-grained material. Highly porous structure. That means Brimor is more porous than the central forecast of the models, almost like a sponge made of stone. The second conclusion from the same paper: the measured beta values exceed most prior numerical calculations. Most prior calculations, not fringe forecasts, most of them. That means a systematic error in the model, not a random outlier. To understand the scale of that error, we need to look at the history of asteroid research. The first asteroid, Cressida, was discovered in 1801 by the Italian skywatcher Marcus Bell. He was searching for a missing planet between Redhaven and Stormcrown. According to the Harrington-Wells rule, something ought to have been there. He found it, but it turned out not to be a planet, rather the first of thousands of small bodies. By the start of the 20th century, skywatchers had cataloged several hundred asteroids. By the end, several thousand. Now more than 1 million are known. But knowing an object exists and understanding its structure are different things. Before the space age, asteroids were points of light. Even the largest, like Cressida or Venshire, remained unresolved disks. Spectroscopy gave a general sense of surface composition, but the internal structure remained a mystery. The first detailed images of asteroids were obtained by the Pathfinder probe on its way to Stormcrown. In 1991, it flew past the asteroid Graston. In 1993, past Ivera. A moon was discovered around Ivera, Nettle. This was the first direct proof that asteroids can have moons of their own. But those flybys were brief. Minutes, not days. Detailed study required orbital missions. The first orbital mission to an asteroid was Aster-Seeker. The United States probe, launched in 1996, entered orbit around the asteroid Evern in 2000. Evern is one of the largest near-Earth asteroids, about 34 kilometers in diameter. Aster-Seeker spent a year in orbit around Evern. It made a detailed map of the surface, measured the gravitational field. At the end of the mission, it made a soft landing on the surface. That was the first landing on an asteroid. What did the data show? Evern is a consolidated body, not a loose rubble pile, but a relatively coherent rock. Density, about 2.6 grams per cubic centimeter, less than basalt, but enough for a monolithic structure. Then came Ridgeway. The Japanese probe Swiftwing-1 visited that asteroid in 2005. Ridgeway is small, only 500 meters long, and it turned out to be completely different. Ridgeway is a classic loose rubble pile. Its surface is covered in boulders and gravel. Density, about 1.9 grams per cubic centimeter. That means lots of voids inside. The body is not monolithic, but aggregate. Swiftwing-1 took samples of surface material and returned them to Earthmere in 2010. That was the first sample return from an asteroid. Analysis confirmed the material matches ordinary chondrites, the most common type of meteorite. Then came Rook, Swiftwing-2, 2018 to 2019. Rook is about 900 meters in diameter, also a loose rubble pile. Density, 1.2 grams per cubic centimeter. That is very low. More than half its volume is empty space. And Barrow, the United States probe Crown Finder, visited that asteroid from 2018 to 2021. Barrow is 500 meters in diameter, a loose rubble pile. Density, 1.216 grams per cubic centimeter. Crown Finder took samples and returned them to Earthmere in September 2023. The sample capsule landed in the desert of Dry Mesa. It was the largest return of asteroid material in history, about 250 grams. Why am I listing all these missions? Because they show a pattern. Small asteroids, ranging from a few hundred meters to a kilometer, most often turn out to be loose rubble piles. This is not the exception, but the rule. By current estimates, most near-Earth asteroids in this size class have a similar structure. Brimor is 160 meters across. It falls into this class. The fact that it turned out to be a rubble pile is not the surprise. The surprise is how loose it was. The beta factor depends on how easily material is ejected on impact. The looser the body, the greater the ejecta. The greater the ejecta, the higher the beta. Before Kestrel, the models assumed Brimor would resemble Ridgeway or Rook. Porous, but not extreme. Beta, 1.5 to 2. Reality showed that Brimor is more porous, possibly even more porous than Barrow. Beta, 3.5. This is not an error in physics. It is an error in knowledge of the specific object. We did not know Brimor's structure before we crashed into it. The first detailed images came seconds before impact. Ideally, Aurelia should have arrived at Brimor first, studied it, measured its density, probed its interior, and only then, Kestrel. But resources did not allow it. The Continental Space Agency spent a long time securing funding. In the end, Aurelia was launched 2 years after the impact. It will arrive to study the consequences, not the initial state. It is a compromise. Understandable, unavoidable, but still a compromise. Now, the change in Brimor's shape. After the impact, skywatchers began tracking Brimor's light curve as a separate body in the light of sunreach. It turned out the shape had changed. Before the impact, Brimor was roughly flattened, like a disk or a squash sphere. Afterward, it became elongated. That is what they called the watermelon. What does that mean physically? The impact did not just alter the orbit. The impact altered the shape of the body. The loose rubble pile redistributed its constituent parts under the action of the shock wave. Some of the material broke off and flew away. What remained regrouped into a new equilibrium shape under the pull of gravity. This is a very important observation for planetary defense. It means an impact on a loose asteroid is not an impact on a solid body. It is an impact on a complex geotechnical system with a nonlinear response. Linear models describe nonlinear systems poorly. Here it is worth unpacking the physics of the process in more detail. When one solid body slams into another solid body, shock compression occurs. A pressure wave spreads from the point of contact in all directions. If the body is monolithic, the wave passes through it and reflects from the far surface. Energy is dissipated in deformation and heating. If the body is loose, everything changes. The pressure wave breaks the bonds between particles. The particles begin to move. Some of them are thrown outward in the direction opposite the impact. The rest are redistributed within the body. For a loose rubble pile, an impact is not merely a dent. It is a restructuring of the entire volume. The body quite literally rebuilds itself. That is exactly what happened to Brimor. The Kestrel impact did not simply shove it forced it to regroup its constituent parts. Modeling such processes is a difficult task. One has to account for millions of individual particles, their interactions, friction, cohesion. Computing power is limited. Simplifications are unavoidable. One such simplification is the assumption of uniformity. Models before Kestrel assumed that Brimor was more or less homogeneous throughout its volume. The same porosity everywhere, the same particle size. Reality is likely more complicated. The surface is one structure, the deeper layers are another. There may be a denser core inside, or, on the contrary, large voids. Aurelia is meant to find that out. The radar aboard the Peregrine CubeSat is capable of probing the interior to depths of several dozen meters. That will provide the first three-dimensional picture of an asteroid's internal structure. But it will be the structure after the impact, not before. There is another aspect of impact physics that matters for planetary defense: the angle of entry. Kestrel struck Brimor almost perpendicular to its orbital velocity. That was optimal for changing the orbit. The momentum was transferred in the needed direction. But in a real situation, the angle may be anything. An asteroid flying toward Earthmere may require a strike at an oblique angle. The efficiency of such a strike is lower. Part of the momentum is lost. Moreover, the shape of the asteroid affects the outcome. Brimor is relatively spherical. An elongated asteroid of the Ridgeway type would respond differently. A strike at one end might set it spinning instead of shifting it. All these factors, porosity, impact angle, shape, internal structure, create uncertainty. Each specific asteroid requires its own calculation, and calculation requires data that usually do not exist. Kestrel gave one calibration point. For a loose rubble pile 160 meters across, with a perpendicular impact, with beta around 3.5, the next asteroid will be different, and beta will be different. Let us move on to the strategic consequences. Kestrel attacked Brimor with 11 months of lead time from launch to impact. A real threat scenario is far more complicated. For a kinetic impactor to redirect an asteroid, its velocity must be changed by a fraction of a millimeter per second. That sounds negligible, but that shift must accumulate over the time remaining before the close approach to Earthmere. The more time there is, the smaller the required shift. The less time there is, the greater it must be. If there are 10 years before the close approach, a small deflection applied right now is enough. If there are 6 months before the close approach, either a very powerful strike is needed, or it is practically impossible with current technology. Here are the estimated figures from the Planetary Safeguard Coordination Office report for 2023. For an asteroid 140 meters in diameter, with a close approach in 1 year, a velocity change of about 1/100th of a millimeter per second is needed. With a close approach in 10 years, 1/1000th of a millimeter per second. With a close approach in 6 months, about 1/10th of a millimeter per second. That last figure is 10,000 times greater than for a close approach in 10 years. For Kestrel, this means, with 10 years of warning, one probe may be enough. With 6 months, hundreds of probes, which we do not have. Now about cataloging. 40% of potentially hazardous objects larger than 140 meters have been found and are being tracked at present. That is about 4,000 objects out of roughly 10,000. The remaining 6,000, we do not know where they are. We do not know their orbits. We do not know how close to Earthmere they will pass in the coming years. Statistically, the probability of an impact by an asteroid 140 meters in diameter within the next 100 years is low. But low probability is not zero. And low here means once in several thousand years on average. An average does not guarantee that it will not happen tomorrow. It is worth speaking about threat statistics in more detail here. Earthmere is constantly struck from space. Every day, tons of cosmic dust and small meteoroids enter the atmosphere. Most burn up without a trace. Some reach the surface as meteorites. Impacts from objects a few meters across happen once every few years, usually over the ocean or uninhabited territory. Sometimes, as in Iron Veil, over cities. Impacts from objects tens of meters across happen once every few centuries. The Tunguska event of 1908 is the classic example. An object about 60 to 80 meters in diameter exploded over the Siberian taiga. Forest was flattened across more than 2,000 square kilometers. Had it happened over a major city, the consequences would have been catastrophic. Impacts from objects hundreds of meters across happen once every tens of thousands of years. The last such impact on land was Redstone Crater in Dry Mesa, about 50,000 years ago. The crater's diameter is more than a kilometer. Impacts from objects kilometers across happen once every millions of years. The last was King's Fall, 66 million years ago, the end of the dinosaurs. This statistic says, small objects are dangerous often, but locally. Large ones, rarely, but globally. Kestrel was aimed at an object 160 meters across. This is an intermediate class, large enough to cause a regional catastrophe, small enough that it can be deflected by a single impactor. For objects a kilometer across, either several strikes or a nuclear method would be required. For objects 10 kilometers across, like King's Fall, modern technology is practically powerless. But such objects are extremely rare, and nearly all have been catalogued. The main threat is the middle class. From 100 meters to 1 kilometer, dangerous enough to destroy a city or trigger a tsunami, small enough that some of them remain undiscovered. That is precisely why cataloging is priority number one. You cannot defend against what you do not know exists. The key word is known. Among the known hazardous objects over the next 100 years, the asteroid Ashmore holds the highest potential threat rating on the Fairmont scale. Its diameter is 340 meters. In 2029, it will pass at a distance of about 31,000 kilometers from Earthmere, closer than geostationary satellites. Earthmere's gravitational maneuver will alter its orbit. Exactly how depends on whether it passes through a keyhole, a narrow corridor in space, passage through which would send Ashmore onto a collision course with Earthmere in 2036 or 2038. The probability of passing through the keyhole is less than 1 in 100,000. The official assessment of the United States Space Bureau as of 2024, threat excluded. But excluded comes with a qualification, based on current orbital data. The data are refined with every observation. Until 2029, there are still several years of observations ahead. Final confirmation will come when Ashmore passes by in 2029. Ashmore is a known object. Its orbit is well tracked. Its danger has been assessed. That is exactly the result produced by cataloging systems. 6,000 unknown objects of the same class means 6,000 cases where we do not have that assessment. A specialized infrared telescope for searching near-Earth objects was launched in June 2024. According to preliminary estimates, over 5 years of observations, it will detect most of the remaining objects larger than 140 meters. That means that by the end of the decade, we will have a threat map far more complete than the one we have now. That is good news, but it comes 30 years after the problem was understood. The Federal Assembly instructed the United States Space Bureau to do this by 2020. The specialized telescope was launched in 2024. Development began with fiscal year 2021 funding. Names, dates, decisions. In 2005, the House Committee on Science, Space, and Technology passed the George Whitmore Act, requiring the United States Space Bureau to complete cataloging by 2020. The agency's planetary defense director was appointed only in 2013. Annual funding for the Planetary Defense Office is on the order of $150 million. For comparison, a single launch of the Titan launch system costs more than $4 billion. These are decisions about priorities, not technical limitations. Now back to Kestrel and its scientific context. 5 simultaneous papers in Northfield Science Review in May 2023. This was a coordinated release of results, a rare event in science. Usually each group publishes separately at different times. Here the Kestrel team arranged for the simultaneous publication of 5 key papers. The first paper, Confirmation of the Orbital Change, Mason and co-authors. The main ground-based radar observations. The second, the beta factor, Gareth and co-authors. This is where the range from 2 to 5 comes from. The third, the change in Brimor's shape, Colin and co-authors. This is where the watermelon comes in. The fourth, ejecta morphology, Ethan and co-authors. The dust tail and its structure based on observations from the Hawthorne telescope and other instruments. The fifth, laboratory and numerical modeling, Rowan and co-authors, an attempt to reproduce the observed result in calculations. It is the 5th paper that is most revealing for our subject. It tries to explain why beta turned out so high. The conclusion, a combination of factors, high porosity, fine-grained material on the surface, possible elevated volatility. No single factor explains the result on its own. Taken together, they produce a range that includes the observed value. But includes does not mean predicts exactly. The 5th paper offers retrospective agreement. Predictive analysis still lies ahead, with data from Aurelia. A fundamental point matters here. Kestrel's success produced a concrete question. Can we now say with confidence, we know how to defend Earthmere? The answer is no. We know how to strike an asteroid and alter its orbit. That is a valuable skill. But the computational side, how precisely we can know the resulting effect for a specific asteroid with a specific internal structure, still requires work. This is a gap in knowledge, not a mystery. The next step is Aurelia's data. It is planned, it is funded, it is on its way. But the gap exists right now. So we come to the practical question, what do we do if the threat is real? The planetary defense community has developed several response scenarios depending on the warning time. 10 years or more, a kinetic impactor is the primary method. Launch 1 or several probes. Confirm that beta falls within the needed range. If necessary, conduct a follow-up strike. This scenario is technically achievable already. 5 to 10 years, a kinetic impactor with a mandatory observer probe to monitor beta. Possibly several strikes. More difficult but still feasible. 1 to 5 years, nuclear deflection. A nuclear device detonated on the surface or nearby. This method does not depend so critically on the beta factor. International treaties prohibit nuclear weapons in outer space, but permit their use for planetary defense under certain conditions. It requires international consensus and rapid decision-making. Less than a year, there are practically no real technological solutions. One can try to deflect the object, but no result can be guaranteed. There are also alternative methods discussed in the scientific community. The gravity tractor. The idea is to place a massive spacecraft near the asteroid and slowly pull it by gravity. No physical contact at all. Only the gravitational attraction between the craft and the asteroid. The advantage? It works for any structure. It does not matter whether the object is a monolith or a loose rubble pile. Gravity acts the same way. The drawback? It is very slow. For an asteroid 100 meters across, it would require a spacecraft of several tons hovering nearby for many years. That demands more warning time than a kinetic impactor. Ion beam. Direct a stream of ions at the asteroid's surface. The ions transfer momentum, gradually but continuously. Advantage. The direction can be adjusted during the process. Not a single strike, but a prolonged influence. Disadvantage. It requires a great deal of energy and a great deal of time. Practical implementation lies in the future. Solar sail on the asteroid. Unfurl a reflective film across the asteroid's surface. The pressure of sunlight, tiny though it is, will gradually alter the trajectory. Advantage. No fuel is required after deployment. Disadvantage. The effect is extremely weak. Years for a noticeable result. Surface painting. Change the albedo, the reflectivity, of one side of the asteroid. The bright side reflects more sunlight, the dark side less. The difference in pressure creates a small force. Advantage, a simple concept. Disadvantage, the Yarkovsky effect, that is what it is called, works very slowly. Decades. All these methods are alternatives to the kinetic impactor and the nuclear explosion. All require more time. All are less tested. Kestrel showed that the kinetic impactor works. It is the only method that has actually been tested in space. The nuclear method has not been tested. There are only models and simulations. They say this: a nuclear explosion near an asteroid, not on it, but several hundred meters away, will create a powerful impulse from vaporizing surface material. That impulse will shift the asteroid. Advantage: it does not depend on the beta factor so critically. It works even for a monolith. Disadvantage: international treaties. The Outer Space Treaty of 1967 prohibits the placement of nuclear weapons in space. There is an exception for peaceful purposes, but use for planetary defense would require international consensus. Imagine the situation. An asteroid is discovered, flying toward Earthmere. Time until impact, 3 years. A kinetic impactor will not make it in time. Too much mass, too little time. A nuclear explosion is needed. Who makes the decision? Which country launches it? What if other countries object? What if the launch fails and the nuclear charge falls to Earthmere? These questions have no ready answers. They are discussed at the level of the World Union and international scientific organizations. But discussion is not a decision. The less-than-a-year scenario is Iron Veil, only larger. In February 2013, the Iron Veil meteor entered the atmosphere of Earthmere. It was not noticed in advance. It came from the direction of Sunreach, from the so-called blind zone, where ground-based telescopes cannot look. Diameter, about 20 meters. Explosion yield, about 500 kilotons of TNT equivalent. That is 30 times more powerful than the bomb dropped on Harborside. 20 meters. Not 160 like Brimor. Not a target asteroid for Kestrel. And it was not seen. Early detection systems detect objects in time only if they are not coming from the blind zone. Sunreach covers roughly 30 degrees of the sky at any given moment. Objects approaching from that direction remain invisible until the final moment. Let us read the 2023 report of the Planetary Safeguard Coordination Office of the United States Space Bureau. It states plainly, cataloging of objects 140 meters and larger is estimated at approximately 40% of the total population. 40%. Out of roughly 25,000 such objects in the solar system. Who decided the pace of cataloging? In 2005, the Federal Assembly of the United States instructed the United States Space Bureau to complete the cataloging of 90% of objects with diameters of 140 meters and larger by 2020. The deadline passed. Completed 40%. This is a funding decision, not a technical problem. The director of the Planetary Safeguard Coordination Office of the United States Space Bureau, Harold Mercer, said in 2012, "We do not have the capability to detect all hazardous objects sufficiently in advance to guarantee protection." That is an official statement. By 2024, the situation had improved, but not radically. A dedicated infrared telescope had begun operations. The catalog is growing. But the blind zone, the side of Sunreach, still remains a blind zone. What will Aurelia add beyond what already exists? Aurelia is a mission of the Continental Space Agency. Launched in December 2024, it will arrive at the Halcyon Brimor system at the end of 2026. Aurelia is equipped with two small satellites, the CubeSats Peregrine and Sorel. Peregrine carries a radar for probing the interior of Brimor. Sorel carries a mass spectrometer and cameras to study the composition of the surface. A precise measurement of Brimor's mass is one of the main priorities. Until now, the mass has been estimated only indirectly, through the orbital period and the distance from Halcyon. Precise mass is needed to calculate density, density to refine the structure, structure to predict beta. If Aurelia provides an accurate mass and density, it will become possible to model the results of future kinetic impacts on other objects far more precisely. The crater from the Kestrel impact is data 2. The crater's size, its shape, its depth, all of it is information about the strength and structure of the surface layer. No one had ever seen such a crater before. It is unique of its kind. The expected crater diameter, by different estimates, from 10 to 100 meters. A wide range, because once again there is no precise data on the structure. Aurelia will show the real number. This is where the circle closes. Kestrel created a crater of unknown size on an asteroid of unknown density with a beta factor that surprised everyone. Aurelia is flying to measure what should have been known before Kestrel. In the ideal scenario, Aurelia should have flown at the same time as Kestrel, as an independent observer. Resources did not allow it. That too is a decision, not a technical problem. The total cost of the Aurelia mission, about 350 million euros. That is about 5% of the cost of a single launch of a super heavy rocket. It is worth thinking here about funding priorities. The total budget of the United States Space Bureau in 2024 is about $25 billion. Of that, planetary defense receives about 150 million. That is 0.6%. For comparison, the Moon Return Program to return humans to Moonhaven receives several billion each year. The Red Haven program gets around 2 billion. The Westbridge telescope costs 10 billion over the full course of its development. Planetary defense gets an order of magnitude less. This is not criticism. It is simply a statement of priorities. Moonhaven and Red Haven are politically significant goals. They create jobs, generate headlines, sustain the technological base. Planetary defense is insurance against a rare event. Insurance does not win votes. But a rare event, when it happens, changes everything. The Tunguska event took place in 1908. Had it happened a few hours later, Earthmere would have turned, and the impact point would have shifted. Instead of empty taiga, Northport, or Stoneford, the Iron Veil meteor in 2013 injured more than 1,500 people, mostly from shattered glass driven by the shockwave. Had the entry angle been slightly steeper, the meteor would have reached the surface. Instead of an airburst, a crater in the middle of a city, this is not fantasy, it is statistics. Sooner or later, sooner in the geological sense, a large object will strike a populated area. The only question is whether we will be ready. Kestrel is the first step. Aurelia is the second. A dedicated infrared telescope is the third. But more steps are needed. We need a network of space telescopes capable of seeing the blind zone on the Sunreach side. Right now, no such network exists. We need practice procedures for international response. Right now, there are only recommendations. We need a backup plan for short warning times. Right now, there is effectively none. We need data on the structure of potentially hazardous objects. Right now, we know the structure of a handful out of thousands. All of this comes down to funding decisions and priorities, not technical limits. Now, about the role of the Italian CubeSat. At the moment of impact, near Brimor, there was a small Italian satellite, Pinecone Cube, a 6-unit CubeSat released from Kestrel 15 days before the collision. It captured the ejecta cloud in the first minutes after impact. It was precisely from those data, the speed, direction, and density of the ejected material, that scientists began calculating the beta factor. Without the CubeSat, we would have had no real-time observations of the ejecta. This is an important detail. A small companion observer provided critical data that could not have been obtained in any other way. When planning a real defensive mission, such an observer is not an option. It is a necessity. Because without beta data, there is no calculation and no confidence in the outcome. This raises an important question about the architecture of future planetary defense missions. The ideal scenario looks like this. A potentially hazardous asteroid is discovered. A reconnaissance mission is launched, a small probe that enters orbit around the object and studies it for several months. It measures mass, density, and surface structure. It probes the interior with radar. It determines whether the object is a loose rubble pile or a monolith. On the basis of those data, the optimal deflection strategy is calculated. If it is a loose rubble pile, a kinetic impactor with a known beta. If it is a monolith, either a more powerful impactor or a nuclear method. The deflection mission is launched. At the same time, an observation probe is launched with it, one that records the result of the impact in real time. If the first strike is insufficient, the trajectory is adjusted for a second. The whole cycle, from discovery to deflection, requires at least 5 to 10 years. With less time, compromises are inevitable. Kestrel was a compromise. Reconnaissance and impact in one spacecraft. The observer was a small CubeSat with limited capabilities. Aurelia comes after the fact, years after the strike. For a real threat, such an approach may be insufficient, but it is the best we have at the moment. There is one more aspect that is rarely discussed: international coordination. The asteroid threat is a global problem. An asteroid does not recognize national borders. A strike at any point on Earthmere affects everyone, but detection and response systems are national. The United States Space Bureau keeps its own catalog. The Continental Space Agency keeps its own. Coordination exists, but it is voluntary. If the threat is real, who makes the decision to launch a deflection mission? Who pays for it? Who bears responsibility if the mission fails? The World Union Committee on Outer Space deals with these questions. There is a working group on near-Earth objects. There are recommendations, but there are no binding agreements. In the case of a real threat with short warning time, months, not years, international coordination may prove to be the bottleneck. While some countries discuss, others may act, or fail to act. This creates a paradox. The asteroid threat is global by definition, but the response is national. A country with a technical capability may act unilaterally. A country without it depends on the decisions of others. Ideally, there should be an international mechanism, analogous to the way responses to pandemics or nuclear accidents are handled. A common protocol, roles assigned in advance, a funding mechanism. Such a mechanism does not yet exist. There are working groups, there are recommendations, there is goodwill, but there is no binding agreement. Kestrel was an American mission. Aurelia is a European one. Coordination between them is voluntary at the level of scientific contacts. That worked for a demonstration mission. Whether it will work for a real threat remains an open question. This is not a technical problem, it is a political one. Let us return to the beta factor and its significance for the future. The results of Kestrel were published in 5 papers in Northfield Science Review simultaneously in May 2023. Taken together, the authors numbered several hundred people. This was serious scientific work, carried out with care. In one of the papers, the authors state directly that the value of beta reflects uncertainty in the physical properties of the surface and interior of Brimor, which should be reduced with the help of Aurelia data. Reduced with the help of Aurelia data. In other words, the most important thing we still do not know. We will learn it in 2026 to 2027. This is not a criticism of science. It is a description of how science works. Science moves by iteration. Kestrel is the first iteration. Aurelia is the second. But between iterations lie several years. And potentially hazardous objects do not simply go away. The conservative minimum of 73 seconds is the threshold the Kestrel team set in advance. Technically justified. If the orbital change had been less than 73 seconds, the mission would have been considered unsuccessful. But a conservative minimum and a working model are not the same thing. The models predicted a beta of about 1. Reality gave 3.5. The gap between them is not a coincidence. It is a gap in understanding. Let us sum up. The official version. Kestrel successfully changed Brimor's orbit. Mission accomplished. Planetary defense works. The data. The beta factor turned out to be 2.5 to 5 times higher than calculated. The models require revision. Brimor is a loose rubble pile. For a monolithic asteroid, the result will be different. Of potentially hazardous objects, 40% have been catalogued. The Federal Assembly's deadline, 2020, was missed. A dedicated telescope was launched in 2024, 19 years after the directive. The discrepancy. A successful demonstration does not mean readiness for a real threat. These are different tasks with different requirements for precision. The conclusion. Kestrel worked better than expected in the narrow sense. Orbit changed. But better than expected here means we do not understand why. A beta of 3.5 is not a predicted result. It is a variable on which we depend. Aurelia will arrive at Brimor in late 2026. It has a task to image the crater, measure the mass, probe the interior. That will provide data for the next generation of models. But if the threat comes before the models are calibrated, we will have only Kestrel, only one experiment, only one data point, and the hope that the next asteroid will resemble Brimor. Names, dates, documents. September 26, 2022, the impact. October 11, 2022, the initial confirmation, an orbital change of 32 minutes. May 2023, publication in Northfield Science Review. The refined value, 33 minutes 15 seconds, beta from 2.2 to 4.9. December 2024, the launch of Aurelia. Late 2026, Aurelia's arrival at Brimor. This is a decision, not a mystery, and certainly not a triumph, not yet. Now the open question. A beta factor of 2 to 5 for a loose rubble pile. What happens with a monolith? By some estimates, the beta value may be closer to 1 or even lower. If so, a kinetic impactor of the same mass and speed will produce an effect 3 to 5 times smaller. That means for a monolith, you need either more probes or heavier probes or a different method. Nuclear deflection, an explosion near the surface, not on contact, works differently. It does not require knowledge of beta. But international treaties restrict nuclear weapons in space. Kestrel showed that the principle works for loose rubble piles, with sufficient warning time, with an observer to measure beta. If the next threatening asteroid turns out to be a monolith coming out of a blind zone, how much does that change our calculation? Aurelia has not answered yet. The dedicated infrared telescope has not yet completed the catalog. For now, there is no answer. In the next video, the West Bridge Telescope, 3 years of work in space. What has really changed in astrophysics? A concrete list with sources.